Okay, so the next session will be on how we carry out inference in predicate logic. Earlier we saw something about inference in propositional logic, so we need to see how to extend that for predicate logic basically. So the topics that we include here is what are the inference rules that we use. For example, we saw that in the case of first order logic there was modus ponens and elimination or introduction and things of that sort. So what are the and of course resolution, and what are the inference rules that we should use in predicate logic, because in predicate logic we have things like quantifiers. So how do we take care of those quantifiers? And we also have relationships, so relations. So how do we take care of that? So that is what we need to see. So what are the inference rules that we can use, and how do you carry out unification? For example, if you have say two different sentences and you have the same predicate, but you have different say variables or constants in that. So how do you unify those? So you need to do some type of substitution. So we will see that. And then to do theorem proving, there are three basic methods which you can use. The first one is called the forward chaining method, and the second one is the backward chaining, and the third one is the resolution based. So the resolution based is extension of what we saw in propositional logic, and we will see how we can use that for predicate logic basically. Okay, so we saw that for propositional logic we had all these inference rules that were available. So for example, modus ponens and elimination and introduction or introduction, resolution. So these are some of the inference rules which can be used, and you have some additional inference rules. So for example, universal elimination, existential elimination, existential introduction, etc. So these are some additional inference rules. Okay, so if we look at this example here, so what we saw in propositional logic was that if you had two sentences, alpha or beta, and not beta or alpha, so if you have beta in one and not beta in the other, you can remove those and you will get alpha or gamma. Similarly, or if you have not alpha implies beta and beta implies gamma, then you will get not alpha implies gamma. So you are removing the beta over there, and you are coming up with a new proposition over here, or predicate if it is a predicate logic. So in the case of predicate logic, you may have, for example, in the end sentences like this. So how you need to have this is that you can have only or in each of these sentences. So it is something like saying not P of W or Q of W, okay, that is one, and P of X or R of X, and not Q of Y or S of Y, etc. So this is what is known as the conjunctive normal form. So you have a conjunction of disjunctions basically, and whatever you want to prove, for example, if you want to prove SA, you have to include not of SA. So you are including the negation of what you want to prove into the knowledge base, and once you do that, you need to take these sentences and you have to use resolution on that. For example, if I take not P of W or Q of W, and I take this one not Q of Y and or S of Y, these two, and I do resolution on this, because you have Q here and not Q here, this will result in not P of W or S of W, and you need to replace one of these variables. So you are replacing y by w over here and you get this one. Then you can take this and unify it with this one, that is p of x or r of x, which is given here. And because you have not p here and p here, you're going, when you unite these, you're going to get s of, you're replacing for w, you're replacing x, so you'll get s of x or r of x. And then if you unify that with not r of z or s of z, you'll get s of z here. And finally, you have included not s of a. So if you put not s of a, you are replacing z by a and you are getting s of a and not s of a, and therefore you will get a nil here. So once you get a nil here, it means that this is true. You need to prove s of a, and if you put not of s of a into the knowledge base and you get a nil, it means that your whatever you want to prove is true. So how do we go about from the beginning? Okay, so you have the first order logic. So in first order logic, we know that there are quantifiers and there are relationships, etc. So if you can convert it somehow into propositional logic, then you can use the propositional inference over there. So that is what is done. So let's say what are the inference rules that we use for quantifiers. Okay. First one is universal instantiation. In other words, you have to remove the universal quantifiers in that. So what universal instantiation says that we can infer any sentence obtained by substituting a ground term for the variable. So what do you mean by a ground term? If you have a variable x and x is a variable, but if it is a term without any variable, then it is known as a ground term. For example, if you have a variable x and you can substitute for x, say John, then you can remove the universal quantifier. So what you are doing is you are saying substitute theta in alpha, okay, which means you are finding a substitution theta in the sentence alpha, okay. So for example, if you have something like for all v, okay, and you have sentence alpha. So v is your variable over here. So you are going to substitute for v some ground term g in the sentence alpha. Okay, so that is what is being done for universal instantiation. So for example, if we have for all x king x and greedy x implies evil x, then what you can do is you can, instead of x, you can put John or you can put Richard, etc. So if you put for x John, you will get King John and greedy John implies evil John, or King Richard and greedy Richard implies evil Richard. Okay, so what you have done over here is you have substituted for x a ground term which is John or Richard or one of those. So the substitution can be, it depends, for each thing you do the substitution may be different. For example, if you, this is a substitution, for x you are substituting John, or for x you are substituting Richard, etc., or father of John. So obviously you can also have a function over there, father John for x. Okay, so these are different substitutions that we have. And then for existential instantiation, what do you do? So you have a variable, so you have to replace the variable by a constant symbol, and that constant symbol should not be used anywhere else in your knowledge base. So suppose you have a sentence alpha and you have a variable v, so you need to replace v with the constant symbol say k, which is not used anywhere else in the knowledge base. So if you have, there exists v alpha, for v you are going to substitute k, in the sentence alpha. So for example, there exists X, crown X and on head X John. If you have, you can remove this exist X and X can be substituted by some particular constant, say C1. So you are saying a crown C1. So crown C1 on head C1 John. So you can replace this sentence by this sentence, okay. So obviously you need to see that all the variables are unique. You don't use the same variable many times. So you say that there is some object satisfying a condition, okay, and what you are saying is that object is object C1, which is some constant, okay. This is what is called the Skolem constant and the process is called Skolemization. So what you find that they are inferentially equivalent. So you could use this in that, okay, though logically it may not be equivalent, it is inferentially equivalent. So for the purpose of inference, you can use this type of substitution. So if you have a sentence like for all X, king X and greedy X implies evil X, and we have these facts, King John, greedy John, brother Richard John. So these are all facts which are there in your knowledge base. You can use the universal instantiation and you can say you are replacing X by John. So you will get King John, greedy John implies evil John, or you can replace it by X is equal to Richard, etc. So this is something which is very general. We'll see how this actually works in an actual example, which we will see later. Okay, so now how do we reduce it to a propositional inference? So suppose we have facts like P1 dash, P2 dash, Pn dash, and we have a sentence here which says some P1 and P2 etc. implies Q. So what you do is you are substituting for Q over here, you are substituting theta, okay, by using what you have over here, okay. So actually you have n plus 1 premises here, so these n premises, and this is one of the premise or one sentence which you have over here. So you are going to apply the substitution theta to Q over here or this sentence here, okay. For example, if I have say individual facts like this, P1 dash is King John and P2 dash is greedy Y, etc. and I have some P1, okay, which is King X, so and P2 is greedy X, which means King X and greedy X is what you have, right? And you can make the substitution X equal to John and Y equal to John, okay, by using these two sentences, okay. So that you are going to put the substitution here so that Q will become evil John basically, okay. So that is how you do some type of generalized modus ponens. That is, you are using more than one sentence here to come up with the inference basically. Okay, now we come to the process of unification, like I said. So for example, if you have variables, okay, you can replace these variables by looking at, for example, if your predicate is nose, you can look at predicates in your knowledge base which is nose, okay, and see whether you can unify this nose John X with this other predicate or this fact that we have, okay. So this is what is known as unification. So you are replacing a variable by a constant over here, okay. So this process is called unification. So when you are unifying P and Q, okay, with the theta, where you are saying substitute theta in P is equal to substitute theta in Q. So in other words, the same theta is used both in P and Q. Okay. So how does this actually work? When you say knows John X, you are going to go down in the knowledge base trying to find a fact which matches with knows John X. Okay. For example, you have knows John Jane, maybe in your knowledge base. So you can unify that sentence and this sentence by putting X is equal to Jane. So let's see how this unification can be done with different sentences. Knows John X and knows John Jane. So what is the unification we have done? We have replaced X by Jane. So your theta is equal to X replaced by Jane. Knows John X, knows Y Bill would be a substitution of X with Bill and Y with John. And here knows John X, knows Y, mother of Y. So Y is actually equal to John, so Y is John and X is mother of John. Now if we take this last sentence, knows John X and knows X Elizabeth, you cannot unify these because you have the same variable X. So same variable X cannot be both John and Elizabeth at the same time. So how do we take care of this? We need to see that you are not using the same variable. So for each sentence that you have, your variable should be different. So suppose I have X here and I have say Z over here, okay, then we can say Z is replaced by John and X is replaced by Elizabeth and it would actually work. So you need to use different variables in each predicate that you use, okay. So you find the single most general unifier, okay, and what you can use. For example, X is John and Y is John are considered equivalent to X is John and Y is X, okay. So this program or the algorithm for unification is given over here, okay. So it can be seen here what has been done. So if there are two, if you are trying to unify one variable and one constant, then you are replacing the variable by the constant, okay. If there are two variables, then you replace one variable by another variable, and if it is a compound X, no, for example, it may consist of 2-3 values, right, X, Y, Z you may have, okay, P, Q, R say. So when you have P, Q, R and they are compound, then what you need to do is you need to see the arguments in this and the arguments in this and choose the first one here and the first one here and unify those, okay. Then the rest of it remains in the list, and then again you have to choose the first one here and the first one there and unify those. So whatever we have just done over here, for example, if you had 2-3 terms here, 2-3 terms here, we first see the first term here and the first term here, and then you take the rest of the list and you choose the first term here and first term here and try to unify those. So that is what is done in this piece of code that we have, okay. So this is actually the unification that actually takes place, okay. If where is replaced by val, okay, then you return, etc. So this is the actual unification that is taking place for a single instance, whereas here you are taking the entire thing and then you are breaking it down and then sending it to unify where. You are sending one of them to unify where to do this, and then it continues with the rest of the terms, okay. So this is the unification algorithm that is basically used. Okay, one thing to be noted here is that if you have the number of terms in this nose and this nose do not match, then it's not possible to unify, right? So you can check that first. You see if it has the same number of terms. If it does not have the same number of terms, then you say the unification fails. So there are cases where it can fail, okay? So you need to also check those. So that's why we have here. So if you are checking all these things and if all these things don't work, then you return failure, okay? So it cannot be unified. Okay, so there are cases where two sentences may not be able to be unified in any way. Okay, so like I said, there are three methods of carrying out the inference, that is the forward chaining, the backward chaining and the resolution. So we will see each of these, and of course we will see resolution in a little more detail. So what are you doing in forward chaining? Okay, so here what you do is you look at your knowledge base which has all these sentences in it, and you have facts which are there in it, and you look at the rules which are there. So for example, if you have king x and greedy x implies evil x, then what you are going to do is you are going to find values for x by looking at the facts which are there in your knowledge base. For example, suppose you have King John somewhere and in another place you have greedy John, right? Then you can replace x by John, okay, on the left side. And if you are replacing x by John, then this it's possible if King John is true and greedy John is also true, then you can imply evil John. Okay, so what you are doing is you are adding new sentences, or you are carrying out inference and finding new inference sentences, and you are adding that into your knowledge base. So you can put evil John and add it into your knowledge base. So what you do is you go down the knowledge base, find the rules and see what new inferences you can get. So obviously it should be in the form of first order definite clauses. Okay, so we need to see that which is either atomic or is an implication whose antecedent is a conjunction of positive literals. Okay, so you have to bring it down to that particular form. So once you go down your knowledge base, go through it once, you will get new inferences, and once you get new inferences, you can go back and do the same process again for a number of iterations. So when you do it second time, you may come up with new inferences, okay? Then you do it a third time till you cannot come up with any more inferences, and then you stop. So you have been able to carry out all the inferences. So in other words, these inferences are what have been entailed by your knowledge base. So once you do that, you can stop, and if the sentence which you want to prove has been inferred, it means that it is true. So let us see one example and see how this is actually carried out. Consider this: the law says that it is a crime for an American to sell weapons to hostile nations. The country No, an enemy of America, has some missiles, and all its missiles were sold to it by Colonel West, who is an American. So this is an example which is given in Russell and Norwich basically. So what we need to prove is that West is a criminal. So how do we get this into the form where we can carry out inference? So we want to prove West is a criminal basically. So these are all the sentences we have. It is a crime for an American to sell weapons to hostile nations. So you need to replace this by the predicate logic. So you have American X and weapon Y and sells X, Y, Z and hostile Z. Okay, so Z is a country, implies criminal X. Okay, so this sentence has been converted into this form. No has some missiles, owns No missiles, M1. okay, missiles M1. All the missiles were sold to it by Colonel West. Missile X and owns no X implies sells West X no. Missiles are weapons. Enemy of America counts as hostile. If enemy X America implies hostile X. West who is American, so we say American West. Enemy no America. Okay, so these are all the sentences which we have got from the passage that we have here. Okay. Then we need to also add that West is a criminal. So criminal West, we have to negate it. So we say not, sorry, we are doing forward chaining. So let's leave it at that. We need to prove that West is a criminal basically. Okay, so what do you do in forward chaining? You need to, like I said, start from the facts. Okay, and see which are the rules it triggers, which means the left hand side of the rules have to be seen whether they are right, okay, whether they can be instantiated. Okay. So here in this particular case, rule 1, suppose we take rule 4, okay, so it says rule 4. So rule 4 is missile X and owns no X implies sells West X no. So here we can put for X we can substitute M1 and owns no M1. So is this true? Owns no M1, we know that that is true. So the left side is true over here. So we can infer sells West M1 no. Okay, so that is something you can infer and you can put it into your knowledge base. And then rule 5 is satisfied with, so rule 5, so we take the rule 5 here, okay, missiles X implies weapon X. So missile M1 implies weapon M1. So we can put it as weapon, we can add weapon M1 also into your knowledge base. And rule 6 is satisfied. Okay, so rule 6 is enemy X America implies hostile X. So, so we need to, so X actually is here no. So enemy no America. So if this is a fact, so this is a fact here on the left, on the, which is a fact. So we can say hostile no, right? So these are the things we can add into your knowledge base, right? And then you go to the second iteration. Okay, when you come to the second iteration, if you take rule 1, okay, rule 1, American X and weapon Y and sells XYZ and hostile Z. Okay. So what are the instantiations we can put here? So American X, okay. So we can put X to be equal to West, weapon Y can be M1 and Z sells, so if we take sells XYZ, okay. So that is also been instantiated here, and hostile Z no has also been instantiated. So we can get the criminal criminal West. So we can add criminal West to the knowledge base, and that is what we need to prove. Okay, so that is how the forward chaining actually works. Okay, and let us look at the proof tree, like they say. This is the proof tree. So you are starting with the bottom here. Okay, so these things which you have at the bottom are the initial facts. Okay, and then this gives the things that you are inferring at the next level. Okay, so you are inferring weapon M1 sells West M1 no, hostile no is what is being inferred. And at the next level you are able to infer by using all these, you are able to infer criminal West. So this is what is known as your proof tree. And you will be able to see that it is sound, okay. It is complete because you are going to come up with everything that you can infer from it, okay. And if k is the maximum number of arguments that you have for any of the predicates, so we can see in this case it's 3, right. P is the number of predicates that you have and n is the number of constant symbols, then you will get no more than p into n to the k distinct ground facts, right. So those are the number of facts which can be inferred from that maximum number of facts. So you can see that once you reach that level, there is no need to go any further. You can stop the iteration at that point in time. So then you say when everything that can be inferred has been inferred and no new inferences are possible, this is what is known as your fixed point, okay. So the fixed point can be reached at that point. So you can say the algorithm would have reached a fixed point and you can stop the algorithm at that point in time. So here is your algorithm for that basically, okay. So you are trying to find phi, okay. So once you find phi, okay, and phi is added on to your knowledge base at every point in time, okay, and repeat until new is empty. In other words, whenever you find a new possible new substitution which you can do and infer something, it's added on to new, and if there is nothing new being generated at any particular iteration, you stop at that particular point in time. Till then you keep repeating this piece of code over here, okay. And one thing to be noted is the standardized variables, so that you don't have the same variables being used. Okay, so if we look at forward chaining, there are some sources of inefficiency here because we are inferring everything that can be inferred, right. We may not want to do that because we only want to infer one statement. So instead of inferring that one statement, if we are going to infer so many statements which are unnecessary, it's going to take time, okay. So the algorithm rechecks every rule on every iteration, okay. So you find that it's sort of very inefficient, okay. So there are three things which can be done here. The first one is what is called matching rules against known facts is one. The second one is incremental forward chaining, and the third one is removal of irrelevant facts basically, okay. So we will see this in the next session, how we apply these three characteristics to reduce the amount of time that is required for forward chaining, and from there we will go on to the backward chaining. So in this session we will stop at this point.